Question 3 on wave motion. A speaker cone is vibrating at a constant frequency, and this causes compressions and rarefactions in air. And we've got our diagram there. Describe what is meant by the terms compression and rarefaction. Well, compression means the air particles are pushed together, so they end up closer together. It's that simple. Rarefaction is when those air particles are stretched apart, if you like, so they end up further apart than what they are, and they're continually vibrating between those two positions to produce the sound waves. B. Sound wave from the speaker has a frequency f of 550 Hz and it travels in air at a speed of 330 meters per second. Calculate the distance from the center of a compression to the center of the nearest rarefaction. Oh gosh, tricky. Okay, so if we represent our compressions and rarefactions with a sine wave, a compression would be here, positive, okay, and a rarefaction would be here, negative, because this is our particle movement. A compression moves one way, positive, and the other way for a rarefaction, negative. So it's actually half a wavelength. That's useful to know. So we can find the wavelength from our formula V equals F lambda. We know the velocity, 330 meters per second. We know the frequency, 550 Hertz. We can just rearrange to find lambda. So that'll give us lambda equals 330 over 550, which equals 0.60 meters. And therefore half our wavelength, which is what we're after, is 30 centimeters, 0.30 meters. That's our answer. Okay, moving on. See, the frequency of the speaker's vibration now increases. State how this, sorry, got distracted. State how this affects the distance from the center of a compression to the center of the nearest rarefaction. So there's actually two rarefactions that are nearest it, obviously one in each direction, but what we're looking at is changes in wavelength. So wavelength does what? So the frequency has increased. The speed, v, or the velocity of the wave, has not changed. So there's no change, keeping it flat. So let's go to our formula, V equals F lambda. We have kept the speed the same on the left hand side. The frequency has increased. What that means is the wavelength, and therefore the distance from the center of a compression to the center of the nearest rarefaction, has had to decrease, okay, by the same proportion. If you times the frequency by 2, you have to divide the wavelength by 2 so that you can keep zero change in the velocity, so the velocity stays exactly the same. Okay. Moving on, D. The speed of sound in air is, where are we, 330 meters per second. The wavelength of the waves produced is 3.7 meters. Calculate the period of the sound waves. Okay. So we have the velocity of the wave, 330 meters per second. We have the wavelength, which is 3.7 meters. That's nice. So from this we could calculate the frequency. Remember our formula V equals F lambda. Got that, could calculate that. And we have to calculate the period. So that's our real unknown, the period. Remember, there's also a formula. The period T is equal to 1 over the frequency. So we have enough information. We can rearrange this equation to find the frequency and then substitute it in down the bottom here. If we do that, we end up with F equals V divided by lambda, which is 330 divided by 3.7, and that gives us a frequency of 89.2 Hertz. Hertz are the units for frequency, remember, and then 1 over 89.2 will give us the period, which is 0.011 seconds. Lovely.